appreciate everybody being here. We have a very special guest here today. I'd like to introduce Dr. Karen Wooley is the W.T. Doherty Welch Chair and of the Chemistry Department and a University Distinguished Professor at Texas A&M University, and she holds appointments in the Department of Chemistry, in the Department of Chemical Engineering, and the Department of Materials Science and Engineering. Most importantly, thanks to Dr. Goodwin, she was also my undergraduate research advisor. So let's give a warm welcome to Dr. Wooley.
Thank you. Thank you, Courtney, for the invitation. I checked my CV, and it's been 20 years since I was here last time. So it was 1999, January 25th, 1999. So just exactly about 20 years ago. And I've seen a lot of changes. So thank you to everyone who met with me today. I really enjoyed the interactions. I love meeting with undergrads. It's rare that I get to meet with so many undergrads outside of Texas A&M University. Of course, at Texas A&M, I interact with a lot of undergrads, right? We have something like 60,000 students. And so we have a really healthy program. If any of you are interested in an REU opportunity or graduate school, let me know later. I'm happy to connect with you. Here's my email address if we don't get a chance to chat this evening. You can see I've changed the title of the presentation that I'd like to give you tonight. What I wanted to do is focus down on a particular topic, and that's one that I'm quite passionate about. And it's general in my lab that we work on functional materials, and often those are nanoscopic, but they almost always involve some kind of macromolecule. And so today what we're going to be discussing is a particular type of nanoscopic functional structure, and that's what we call a hybrid inorganic organic nanoparticle. And these were designed back after the Deepwater Horizon oil spill in 2010 in order to address the issue with environmental pollutants. So again, here in the title, we take attention to the environment. Also, there's a lot of work in my lab that involves the development of materials for biomedical applications. But here today, we're going to talk about health in a different aspect, and that is related to sustainability. And I'll explain that in just a moment. So these hybrid organic nanoparticles were meant to have two different functions. One was the organic material is meant to interact with the pollutants to cause them to be taken into the nanoparticle and capture the pollutant molecules. And then the inorganic component is meant to have a magnetic response to allow for magnetic recovery. And as I said, these materials were developed after the Deepwater Horizon oil spill, where we recognized that there were challenges associated with cleanup. And a couple of those might be able to, I don't know if we can dim the lights a little bit here or not. You might be able to see here, this is a water body that has been polluted, oh thank you, with crude oil. And what you see here is underneath these lily pads, submerged beneath the surface, there is a pool of oil that's not accessed from the surface. And also on the surface here, there's this thin layer of sheen of oil that's residual. And each of these populations are difficult to clean up. So again, we designed these nanoparticle systems, and I'll come back to the design of these in just a moment. But let me come back to the health and sustainability part. And that is that we're building these particles where the organic components are derived from natural products. So we use glucose heavily as a building block to produce polymers that have function and then combine them together with other entities, including, say, these magnetic inorganic particles. So that's the theme of the story I want to tell you today. But as I was discussing with some of you today, a little bit of my philosophy, and that is that I think that chemists are control freaks. Like we like to control everything. And I would say that chemists seek to both understand and control matter at the molecular and atomic scales. And if we contrast that with synthetic chemists as a specific focus area, design and build molecules. And if we then extend that beyond a simple, not a simple, but a typical synthetic chemist to particular polymer chemists operate on building big molecules, so macromolecules or polymers. And sometimes those extend into the nanoscopic regime, and then those are nanostructured materials. And there's really, in my view, not much interest in building something unless it has function, unless it can do something. And so that's been what we've been focusing on for the last 26 years in my lab. So let me go a little step back for those of you in the room who are not familiar with polymers and just schematically go over this concept of going from a small molecule to a macromolecule. And I want to illustrate this in the case of some materials that you're quite familiar with. One of those is glucose or other sugars, and this can be cast out into thin films into what's called sugar glass. And sugar glass has the individual molecules held together through relatively weak interaction, so it can be broken quite easily, as you can see in this case that's often used in the movie industry. If we take those individual glucose small molecules now and connect them together through covalent bonds, where each glucose repeat unit is connected through the 1 and the 4 position, then we have some n number of glucose repeating units, which would be illustrated by several glucose monomers connected together into this covalent framework. And that converts individual monomers into polymers. And you know that cellulose is the structural building material of wood, and it's quite difficult to break, and you can see that illustrated here as well. Now, if we go beyond these natural examples to a synthetic polymer material, this is the chemical structure for Kevlar, and this is polyaramid, where the amide linkages are connected in the para positions of each of the aromatic rings along the backbone. So these polymer chains can interact well with each other, they can crystallize, and they can also be reinforced through inter- and intramolecular hydrogen bonds. And Kevlar is a material that you might also be familiar with as an anti-ballistic material. So this is a very old photo that's just kind of funny with someone testing out potentially some kind of a Kevlar vest. But now if we look at the chemical structure of Kevlar and compare that with Nomex, I want to play this video, and I'm going to see if if you guys can actually hear it. So it's going to come through my computer only. Oh, thank you. And I'll try to paraphrase if you can't hear it, so we'll just be real quiet for a moment. Okay, could you guys hear that? He was talking about Nomex reinforced with Kevlar, how it can stop a knife, it can stop a bullet, but it's expensive, okay? But actually, Kevlar and Nomex aren't that expensive. So these are the chemical structures. Here's Kevlar, I'd already shown that to you. Nomex is a polyaramid as well. The difference between Nomex and Kevlar is simply that the repeating units here have the amides connected through the meta position. So there are kinks along the backbone of the chain. On a macroscopic level, you can think about those kinks as preventing those chains from interacting well with each other, prevent them from crystallizing. So Nomex is a bit more flexible, a bit more soluble, a bit more processable than Kevlar is. But combinations of Nomex and Kevlar are used in various applications, including things like the UGG glove. Does anyone have an UGG glove? No? Okay. Fireproof clothing for firefighters and things. Okay, so these are really important materials. And these are quite simple structures. You see, these are just aromatic rings and amides, right? If we take a look at this process of connecting monomers together to make polymers, that process is called polymerization. And both Nomex and Kevlar are homopolymers, so that means all of the repeating units are the same. Homo meaning the same type. And so these linear homopolymers are the simplest kinds of structures. And even with that simple composition and that simple structure, the polymers can have important functions. Okay, so this covalent polymerization involves this transition, like I said, from weak intermolecular interactions to strong covalent bonds. Okay, but there's an abundance of opportunity to have copolymers. So copolymers have multiple compositions in the repeating units along the backbone. So if we have just 2 different kinds of repeating units, then those could be organized in a variety of different sequences. The 2 extreme cases would be each repeat unit alternating. So we have, say, an A type of composition, then a B, then an A, then a B. And that alternating copolymer would have very different properties than the other extreme, where one of the repeating units is in a sequence together, and then it transitions over to the other type. So this would be called a block polymer structure, because there's a block of one type connected to a block of another type. We focus in my lab to a great extent on using block copolymers in order to have different properties within different regions of the molecule to drive phase segregation events, which then drives the formation of nanoscopic objects in rather a controlled way. So I also discussed with people today that often polymers are considered to be plastics, and people think about plastics as being quite simple materials, but I like to call them sophisticated, because even a garbage bag has a high degree of sophistication and the kinds of layers that are involved, the kinds of chemistry and engineering and physics that goes into the construction of these materials to provide that barrier. If we look at where polymers are also found, it can be in high-end applications like airplanes, and that provides a barrier and also mechanical integrity. And then a completely different direction is that signaling molecules can be incorporated into the polymer, or the polymer itself can be a signaling molecule. It can be optically active, and that can lead to, say, organic light-emitting diodes and other applications. So overall, I would say that there's a significant interest in the chemistry community in defining the polymerization conditions that take a series of different kinds of small molecules and link them together into these elaborate architectures, because we can build into that structure of programming for the properties and performance of the ultimate materials. And we're not limited by just doing polymerizations. There can be other chemical transformations. So a polymer can be made and then it can be chemically modified, and you can do that in an iterative fashion in order to build up complexity. So in my lab, we focus on developing synthetic strategies. Sometimes it's just fundamental studies of how far can we push what's known in terms of chemistry to build molecules. But usually we have some idea, some kind of application that motivates those synthetic designs. And then we incorporate function to meet those applications, and then we spend a lot of our time on characterizing the materials and testing their performance. Okay, and I just want to show you one example of how diverse this process can be. And that's for just one single type of what we would call an ABC tri-block polymer structure. So it has 3 different kinds of repeating units. And one of those ABC tri-block, what we would call a terpolymer, now because there's 3 different components that we've studied quite a lot, is one that's based upon polyacrylic acid in one block region connected to a polymethyl acrylate repeat unit, series of repeat units, followed by polystyrene. And when we break down the properties of each of these 3 pieces, what we find is that polyacrylic acid is the super absorbent hydrophilic material that's found in baby diapers. Polystyrene is styrofoam, and these have very different properties. So styrofoam can hold hot water, whereas polyacrylic acid absorbs that water. So when these 2 parts are separate from one another, they would separate like oil and water would do. But now that they're connected together with intermediate sequence of polymethyl acrylate, which is intermediate in its hydrophilicity or hydrophobicity, so how water soluble or insoluble it is, but also it has a glass transition temperature that's a little bit below room temperature, so it's flexible and fluid-like at room temperature. So when those 2 pieces are connected by that intermediate region, and that's put into water, under certain conditions where in many cases we have, say, a diamine that can form salt bridges with the polyacrylic acid repeat units, then multiple copies of those polymers can aggregate together into a micellar form, which can be a spherical entity. And it's shown schematically here, but in this transmission electron microscopy image, you also see all of these circular images. So transmission electron microscopy is a process where the sample is on a grid, and then electrons are bombarding that, and we look at the transmission of the electrons through the sample. And so different densities of matter block the electrons to a different extent. So we look at what transmits, and that's what gives the contrast here. So you can see that it's a two-dimensional imaging technique. In a moment, we'll see a three-dimensional tomographic image. But by transmission electron microscopy, we see circles. We do other characterization studies to confirm that this is actually a sphere. Under different conditions, then, the assembly process takes place to, instead of just forming a simple sphere, to allow for elongation of that multimolecular micellar structure into what we show schematically as a cylindrical or rod-like structure. You can see in the TEM image now, we see these elongated fibers. Under still other conditions where we vary, say, the amount of the diamine or the solvent that's used together with water in the assembly process, now a toroidal morphology is seen here, both schematically and by transmission electron microscopy. And finally, we've also been able to form disks. And so it looks like, well, this is just fundamental work, but in fact, now we're translating each of these different kinds of morphologies into different kinds of function. And so to do that, then we incorporate functionality within certain regions of these materials and then test how the materials behave. Okay, so that's a lot about nanoparticles and different kinds of nanomorphologies, and I think everyone in the room is probably familiar with the term nano, but I just want to remind you what something means to be a nanoscopic. So the term nano just means 10 to the minus 9. That can be a nanosecond in time or a nanometer in distance. And I'm still amazed to think about the size of these particles that we're making in the laboratory relative to the size of humans. So if we take a 100 nanometer size particle and multiply it by 10 to the 7th, we get to 1 meter. And that's about the size of a small child. And if we then multiply a 1 meter person by 10 to the 7th, then that would get to the size of the Earth. And so the size of these particles we're working with is comparable to humans as we are to the Earth. So the first photo was one of my sons about 20 years ago or so. And then this is a more recent photo. And this one right here actually is studying to be a firefighter right now. So that makes me more interested in Nomex and Kevlar. Okay, so I want to talk about, just for a moment about some of the targets that we're working on in my lab. Because again, we often look for an application that has an unmet need and design a material to meet that need. So I mentioned that we work on biomedical materials, and we are focusing to a large extent on nanoparticles that are capable of carrying both therapeutic agents and also imaging agents, so we can track the position of the particle and also deliver therapeutics. And we're treating infections and metastases in the lung and also infections in the urinary tract. And we're building those particles out of sugars and other natural products so that after they've delivered their cargo, they're able to break down and be bioresorbed. Now, we're not only able to take these small natural products and build them into an individual nanoparticle morphology, we can also make macroscopic materials. So we've studied the conversion of quinic acid that comes from coffee beans and other sources into large objects that have mechanical properties that can vary from, say, cartilage to bone, and we're looking at those for orthopedic applications. I'm going to talk to a great extent about our nanoparticles that are the hybrid inorganic organic materials, so we'll come back to that in a moment. But we can build macromolecular structures that are not only linear homopolymers like I showed, or linear block polymers, but we can also control the total architecture of the material. We can make tree-like structures that can be aligned on a substrate and be used as molecular pixels for the fabrication of ultra-high resolution microelectronics devices. And we're working on that with Dow DuPont. We've also been studying anti-icing and anti-biofouling polymer materials, and these are meant to be heterogeneous in their topography and their composition, so they don't allow for organisms to adhere over a large surface area. They also organize water molecules, so it inhibits the ice crystallization, and that then suppresses the melting point and suppresses the freezing point of water. Okay, and then more recently, we've begun looking at other strategies to clean up water by using not a nanoparticle that captures the pollutant, but rather a membrane-like material that can either inhibit pollutants from passing through or capture those pollutants so that clean water can be captured from in a flow system. And then what we found was that these materials are quite interesting in that they can basically prevent bleeding by acting as hemostatic agents. And we just submitted a manuscript on that topic that I can share with anyone who's interested in that. Okay, but we're just going to focus on this one particular target application today. And as I said, we started this project after the Deepwater Horizon oil spill in 2010. And what we noticed was that there were typical techniques in place to deal with some of the oil, but then there were those residual issues. And one of the first techniques that's deployed are these booms that are put out to contain the flow of the oil away from the spill site. And then there are pumps that can be brought in to withdraw that oil that's floating on the surface. So that's for the bulk recovery. And then there's these other issues, the submerged oil, and then also the residual thin layer of oil that remains as sheen. Okay, and the way that the residual oil can be captured is to use these mats that are typically polyethylene or polypropylene, and these can be laid out on the surface of the water and then absorb the oil through hydrophobic interactions between the polyethylene or polypropylene and the hydrocarbons that are present in the crude oil. Now what you see is that these aren't very efficient because only one face is in contact with the polluted water system, and they're floating, so they're not getting the submerged oil. And then also you can see it's quite a laborious process. These workers had to lay out these mats. They have to wait for them to absorb the oil, and then they can come in and bag them up and haul them away. And so we thought, well, there must be a better solution, and perhaps that a nanotechnological device could perform better. And one of the things that we were hearing about when the Deepwater Horizon oil spill occurred, and you guys were barely born, right? No, you were born. Okay, sorry, that was only 9 years ago. I was thinking it was another decade. Okay, was that after there were these millions of gallons that they just couldn't deal with. So what they were doing was putting out dispersants. Did anyone hear about this in the news? So they were putting out dispersants. These are surfactant molecules. They're basically detergents, and they were meant to break up the oil into little droplets that could be bioremediated by microorganisms. Okay, if you have a polluted environment and you add more pollution to the polluted environment, that's not the ideal situation. And so we thought, well, if we could put out some kind of a dispersant that would break up the oil and sequester it and capture it like the dispersants were meant to do, but instead of remaining present in the water system, if we could recover them, say by magnetic action, then we could collect those, extract the oil from them, and then recycle them and reuse them in a cyclical fashion. So that was the expectation, and there were two talented students who took on this goal. And Adriana was the first student who began this project, and she designed a system that was expected to have a morphology just like is shown here, where inorganic particles would be contained within an organic framework. And she designed that to be formed by the co-assembly of those block polymers that undergo the multimolecular assembly process, but capturing the inorganic magnetic particles within that organic framework during the assembly. And I'm going to show you, this is a series of transmission electron microscopy images now that are captured with the sample tilting at various angles. So then those can be three-dimensionally reconstructed into a tomographic image. And what you'll see is that, well, let me tell you first, that if we look at just a single two-dimensional image, we can't tell whether the inorganic particles are on the outside or the inside or a combination of both. But with this three-dimensional reconstruction, and I don't know if you can see it very well, but you can see that we can in fact confirm that the inorganic particles are within the organic framework. And these were assembled by a simpler structure than that tri-block I had shown you earlier. This has the polyacrylic acid from baby diapers and the polystyrene of styrofoam cups, but they don't have that intermediate polymethyl acrylate region. And so that makes it cheaper, easier to produce this polymer. And it's produced by polymerization of a precursor to acrylic acid that's not shown, but then styrene. So two different monomers, and then a chemical modification reaction leads to this diblock. Okay, but if that diblock polymer is not co-assembled with the inorganic particles, but rather is assembled in a multimolecular fashion into just an organic particle structure, and then cross-linked throughout the shell to lock it into place, then it can be used as an organic particle to capture the pollutants, but then we have to incorporate the magnetic responsivity. And so Jenny went about forming what we call magnetic hybrid networks, where she took these pre-assembled organic particles and coupled them onto a magnetic inorganic particle. So this is just amide bond formation between an amine on the inorganic particle and carboxylic acids on the organic particle, allowing for these to couple together. And it's really small, but in the transmission electron microscopy image, you can see the different heterogeneity there. Some regions look really dark and others light. The dark regions are where the electrons are being blocked by the inorganic particles. The light regions are the organic particles, and you can see that they're connected to one another. Okay, so then these were each tested for their ability to capture crude oil from an aqueous environment. And I'll show you some movies of this process in just a moment. But in Adriana's case, her particles could take up 10 times their mass. So 10 times the mass of crude oil collected by these particles and captured by magnetic recovery. Whereas in the case of Jenny's materials, they were only able to take up 4 times their mass. And so Jenny got a little bit more aggressive with her system, and she began shaking and even vortexing the samples. And then she found that she could take up 30 times the mass. But then she was forming emulsions. And I want to show you the emulsified phase, which is magnetically responsive. And you can see this is a real-time video. I'll get it to play. And that's a magnet, and she can simply drag the emulsion around the vial. So they're highly magnetically responsive. Okay, so we were pretty happy with ourselves, right? We had this ability to take up 10 to 30 times the mass in crude oil. And then we started asking the question, okay, how much can we recover and recycle over and over again? And when Jenny did some quantitative analyses, she found that she could recover about 90 to 95%. We thought, well, that's pretty good. But then we started thinking, even though this is comprised of polyacrylic acid and polystyrene, the baby diapers and the styrofoam, we're losing 5 to 10% of the material. We're not recovering it. And that comes to our need to be environmentally more aware of the potential adverse effects of the materials that we make and put into the environment. And so how many of you have heard about the Great Pacific Garbage Patch? Only a few? Okay. Oh, okay, a lot. Yeah, so the Great Pacific Garbage Patch, it's a big problem because this is about a year ago, the data where it's expected to be, or guesstimated to be comprised of almost 2 trillion pieces of plastic. It's 3 times the size of France and floating around the Pacific Ocean between California and Hawaii. And so this is some of the plastic that we can see. I'm sure you guys have seen plastic pollution other places around the world. But there's a lot of plastic that we can't see. And so have you guys heard about microbeads as well? Right. So microbeads, again, this is a year-old information here, that plastic microbeads were then no longer able to be used in cosmetic and personal care products in the UK in terms of the manufacture. And they expected a year ago that the ban on sales would follow in July. And these microbeads are used in things like exfoliating face scrubs, toothpaste, other kinds of products. and they wash into the environment. You may have heard about the sea turtles, the baby sea turtles that have been found with microbeads in them. And in fact, ahead of the projected July timeframe, in June, the ban on the sale of the products in the UK came into force. And so it's a big issue to deal with both what we can see and what we can't see. And so what my lab's been doing, probably even since Courtney was in my group, right? We've been thinking about the degradation of polymers. But our focus was more on the function, right? I even started this talk by saying we want to make things that do things. But what I encourage you all to think about is that we shouldn't just be thinking about taking some starting material and producing some functional whatever it is, but we have to think about what happens when it's lost in the environment, what happens after it's performed its function. And we should be concerned about the potential for degradation. We should actually build in opportunities for degradation. So even if materials aren't meant to be degradable, for instance, do you guys know what this material is? Bisphenol A polycarbonate, right? It's found in football helmets, eyeglasses. It's probably still used in some drinking glasses and water bottles. It's no longer allowed to be used in baby bottles and things. And that's because it's a perfectly great material. It's a great engineering plastic. But when it's, say, put into an extreme environment, like a dishwasher, at the elevated temperatures and high pressures with that hot water blasting upon it and the presence of detergents and things, these carbonate linkages along the backbone can undergo hydrolysis and release bisphenol A, and that's been implicated in cancer and other diseases. And so you want to worry about, okay, even if this is not meant to degrade, what could it produce when it undergoes degradation? And so we want to have degradation products that are biologically benign, environmentally resorbable, but also in many cases beneficial. And so what we're doing is, again, building from the very early stage the opportunity to break back down into the monomer building blocks. And that's where we're using renewable resources, natural products as the monomers to build up these functional polymers. So that addresses the issue of what happens to the material when it's lost, so the pollution problem. It also then enhances the sustainability because it relieves the dependence upon petrochemical feedstocks. Okay, so in my group we have several different natural products that we've been focusing on. One of those is glucose. I've already indicated that. We've developed synthetic methodologies by which to transform glucose into linear polymers. We're focusing on polycarbonates so that upon breakdown, what's generated is the sugar plus any chemical modifications we've done to it and carbon dioxide. So we can produce these linear polycarbonates by condensation, polymerizations. I'll show you some chemistry to build up linear polycarbonates by a controlled polymerization process, which is a chain growth process, so we can initiate, grow the polymer, and then terminate in a meaningful way so we can control everything about the polymer structure. That then allows us to build in block polymer structures, and I'll show you that chemistry. I've already mentioned that we use quinic acid as a building block. It's become a little bit expensive, so we've shifted to some extent away from quinic acid, but it has its ability to make cross-link networks with a broad range of mechanical properties depending upon how we do the cross-linking reaction. Then we've used phenolic kinds of natural products, so ferulic acid, quercetin, hinokiol. Hinokiol is a cool structure. It comes from magnolia plants, and it has phenols for reaction to form a carbonate, to make a polycarbonate, and then dangling off as side chain groups of these alkenes. And you know you can do a lot of chemistry on those carbon-carbon double bonds as well. And then finally, we work also with amino acids and making polypeptides. So that's kind of a summary of some of the monomer building blocks we're using. These are some images of some of the products that have been produced in the lab, just to show you a variety of different properties. So they can be rigid materials, they can be flexible, they can be brittle, they can be ductile. They're generally transparent, sometimes they're opaque. So there's a broad range of potential properties, which means a broad range of applications. We can also form them in various molds, so different fabrication methods to control the size and shape, making these super cute little hexagons. Okay, so this comes to another movie that I want to show you, and it's going to be difficult to follow. Turns out actually the audio and the video aren't so well matched up. But this is a clip from Sabrina that's going to talk about sugar plastics. Okay, there's one more, sorry. So this is the one where he says you'll probably be able to eat it. And I just want to show you some of the properties of polymers that I think you're familiar with. I think in this particular clip, the polymer they're using is plexiglass, which is polymethylmethacrylate. It's not actually a sugar polymer, but you can see.
Look at this stuff. You fly in a plane made of it, you wear a suit made of it, and the full wind through that you'll probably be able to eat it. We're organizing Larrabee Plastics. Larrabee Construction is ready with the blueprints. Larrabee Shipping has bought 9 more freighters to handle the traffic. You mean the wheels are in motion already? That's exactly what I mean. Would you mind demonstrating the weight test to Mr. David, please? Oh, Linus, I'll take your word for it. Off you go. Now, wait a minute. I want you to see how resilient it is. Fountain, please, ladies. Some plastic, eh?
So this may be part of why plastics really have taken off. And you find them in everything about everyday life. So I just have to disclose that I actually did start a company about a year ago. It's called Sugar Plastics. And we're developing these sugar polycarbonates for high-end applications. But there's also an interest in addressing, again, this issue that comes with the Great Pacific Garbage Patch and other pollution. And that's typically from throwaway plastics, say single-use plastics, like packaging materials, plastic bags, etc. There was recently on Facebook or Twitter this whale that died, and it was just filled with plastic bags and things, right? So there's this issue for commodity, cheap plastic materials to be made that will degrade into bioresorbable degradation products. So there's another company that's been formed called Acxiom Technologies, and they're really going after this global issue of the plastic pollution problem in terms of packaging materials. So these are just getting off the ground, but when some of you graduate in the future, you may be able to find some startup opportunities for employment. Okay, so let me come back to our central theme, which was meant to be those nanoscopic particles that have an organic framework for capturing crude oil, and then inorganic particles to be magnetically responsive. And May is the most recent PhD student who's working on this, and she's bringing everything I've told you together into one story, where she's starting with glucose, or in this case, alpha-methyl glucose, and transforming that into a couple of different monomers, and I'll show you the chemistry for that in just a moment, and then conducting polymerization in order to build up this polyglucose carbonate, where she can have as side chain groups either just ethyl carbonates as hydrophobic moieties to capture the hydrophobic pollutants, or dopamines, which can interact with the iron oxide nanoparticle in order to facilitate its packaging within the organic polymer framework, again to make these hybrid nanoparticle systems that are again designed to be deployed for capturing pollutants in an aqueous environment and magnetically recovered, followed by degradation. Okay, so the chemistry to make these polyglucose carbonates, as I call them, is one where we wanted to have control over the polymerization. So we can have an uncontrolled polymerization in some sense and not be able to to control how big the polymer gets or its properties exquisitely, or we can have a controlled polymerization. And to have a controlled polymerization, we have to be able to start the polymerization and stop it. And to start and stop it, we need to have the requirement that an initiator be used to initiate the polymerization, and then a terminator be used to terminate it. And to do that, we need a monomer that won't react with another monomer itself. So if monomers can react without the initiator, they can just combine with each other. So instead, what we do is we form this cyclic carbonate here, and that won't react with another cyclic carbonate. So that's stable. When we add an initiator, it will attack this cyclic carbonate, open it up, and that then creates another site that can attack another cyclic carbonate that can attack another cyclic carbonate, etc. So it propagates the chain and builds up this polymer, this polycarbonate. And so that chemistry was developed actually several years ago now by Koichiro Mikami, and has been followed up by a couple of other postdocs and PhD student teams in my group. And one of those is Lu Su. And what Lu recognized was this possibility to install various kinds of R groups here to control the properties of that polyglucose carbonate. So in one case, she would install just these ethyl carbonate groups, again, just to have those sites blocked, and blocked with something that's hydrophobic, but also hydrolytically degradable. And she does that by starting from a commercially available starting material, where for the sugar numbering scheme, this anomeric position is the 1 position, and then this is 2, 3, 4, and then this is the 6th position, because it doesn't really have a 5. And so when the 4, 6 positions are tied up into a benzylidene, this is just a protecting group, it's an acetal protecting group, then that leaves only a 2 and 3 position open. So reaction with ethyl chloroformate puts into place these carbonate groups. And so if she did this reaction at 0 degrees, then both of these hydroxyl groups would react, and ethyl carbonates would be installed at both the 2 and 3 positions. After that, then she could remove the benzylidene protecting group, freeing up the 4 and 6 hydroxyls, and then bring in the carbonyl and form that cyclic carbonate. Okay. If instead, this is a very simple tweak, if she lowered the temperature during the reaction to -78 degrees, then that reaction with the ethyl chloroformate preferentially reacts at the 2 position. The 3 position is more sterically blocked and it doesn't participate. What that means is she could isolate this initial product, then bring in a different chloroformate. This one has a propargyl group on it, so it has an alkyne. Elevate the temperature to 0, and then that 3 position would undergo reaction. So she could have an ethyl carbonate in the 2 position, a propargyl carbonate in the 3 position, and then removal of the benzylidene protecting group opens up the 4 and 6, where she could install the cyclic carbonate. So from these 2 different monomers, she could do a ring opening polymerization here to have just hydrophobic ethyl carbonate side chain groups, do the ring opening polymerization here to have one ethyl carbonate as just an unreactive entity, and the other, a propargyl group, as a reactive moiety. Okay, so now coming back to May's work, what May's able to do is use as an initiator an alcohol, where that alcohol carries an ethylene oxide polymer. So this is a polymer that's hydrophilic, it's water soluble. You'll find PEG in all kinds of things, even Dasani drinking water. I think it's maybe kind of antifreeze or something. But she could do the ring opening polymerization of these monomers and generate either a copolymer, or in this case, if she does polymerization of 1 followed by the 2nd, then she could make a segment of this kind of polyglucose carbonate having the propargyl side chain groups, and then this polyglucose carbonate lacking those reactive functionalities. So as she's labeled here, this is meant to be a hydrophobic block for trapping the oil, and this is meant to be a reactive group for chemical modification. Since I'm running short on time, I wanted to show some of the analytical techniques we use. So as organic chemists, but polymer organic chemists, we do things like infrared spectroscopy, proton, carbon NMR, phosphorus NMR if we have phosphorus in there, fluorine NMR if we have fluorine, etc. And then we apply unique techniques. So instead of HPLC, like you might find for small organic molecules, we use a chromatographic method called size exclusion chromatography. And size exclusion chromatography separates molecules based on their size, just as the name says. Big molecules are excluded, so they pass through the column quickly. Small molecules migrate in and out of the pores, and they're retained in the column for a longer period of time. So when you look at an SEC trace that is presented as time or retention volume, big things come out earlier than smaller things. So these are some solvent signals, and then here we have the starting macro initiator, and then here's the block polymer after growing those two segments. And the narrowness of these peaks indicates that the polymerization was well controlled. The shift to shorter elution time indicates that the polymer is longer or occupies larger size after the chain extension. So it's just a proton NMR spectrum to show that we can map out all of the protons, and that helps us figure out if we know how many repeat units we start with here, we can say compare to the proton signal here and figure out how many of these repeat units were added. Then we can look at the ethyl proton signals and then figure out how long the next chain extension proceeded. Okay, so what May first found was that first polymer, she couldn't co-assemble it directly with iron oxide nanoparticles as Adriana had done. Rather, she observed phase segregation. So you can see this precipitation and some things floating in the solution. And so what she had to do was think about chemically modifying the backbone of this polymer to have better interactions with the iron oxide nanoparticles. And that's where she installed the dopamine groups for the catechol moiety, the bisphenol, to interact with the iron oxide particles. And so that chemical structure is shown here. So again, she's got the polyethylene oxide that she started with as a macroinitiator, the block polymer structure, and now with the portion of those propargyl groups, she does what is a thiol-ion reaction to bring in side chain groups to which the dopa can be connected. Now she has great co-assembly of the particles. She can characterize them by transmission electron microscopy, also dynamic light scattering, where we measure the hydrodynamic diameters. We get a number average, volume average, intensity average, hydrodynamic diameter of these particles. And here's where I wanted to show you the videos of the process of capturing that crude oil. So I think these will animate automatically. Yeah. So she's added crude oil to a petri dish containing water, and now she's going to sprinkle in those composite hybrid inorganic organic materials that she made. And what you can see is they immediately start breaking up the oil. Okay, and they're basically breaking it up and absorbing it. And then in the next animation, she puts a magnet underneath the petri dish to show that everything's now magnetically responsive. Okay, and they're pretty effective at capturing the oil. And in fact, she's run through this process through multiple iterations and found that she could extract the oil by washing with ether, for instance, and that she could retain a reasonable loading capacity for these materials in a cyclical fashion. Okay, so as a summary of what May's been able to accomplish is that she's repeated this crude oil loading capacity test. She's looked at the recyclability and the loss of material. And with that loss of material, she's also conducted degradation studies, both in organic solvents and also in aqueous media, to confirm that these do break down over a matter of actually several months. It's not a rapid breakdown for the materials. Now she's going to be looking at investigation of installing cross-linking within various portions of these morphologies in order to reinforce the assemblies. Okay, this is where I'm going to conclude with a message to you guys that I've been expressing throughout the discussion today, and that is that I encourage you, no matter what path you pursue, to always think about the ultimate impact of whatever it is you do. And if you're going to be making materials, whether they be organic, inorganic, small molecules, macromolecules, whatever, I encourage you to think about the whole life cycle. And I want to express this in terms of recyclability that we find in nature. So in the animal world, recycling occurs because animals eat other animals, right? So things don't necessarily go to waste. Animals also eat plants, right? And plants, in fact, eat animals. And both animals and plants eat minerals. And even in the mineral world, there are geological evolutions that occur in recycling of materials. So we have to always think about not making something that's ultimately going to persist for long periods of time beyond its useful expectation. I try to point out the people in my group who had done the focus of the work that I discussed. This is a photo of my group from about a year ago. I'd like to also highlight that most of the work in my lab is supported in some way through the Doherty-Welch Chair in Chemistry, and I'd like to acknowledge the Welch Foundation for that. The National Science Foundation has been critical in supporting a lot of the fundamental work we do, and toward the biomedical directions, which I didn't really get into, support comes from the NIH. Finally, if I have a few minutes, I wanted to talk a little bit about my advice to you guys and some of the aspects of the pathway that I've taken over the years. My advice always is to follow your passion and curiosity. Don't end up in a direction where you're not happy and you're not excited by what you're doing. Always question the unknown. I mean, always think to yourself, you know, I don't know that. I should find out the answer. And you guys are lucky that you have Google, whereas we used to have to spend hours in the library, right? And I would say don't be discouraged by failures. Failures are sometimes the best thing. You can learn more from failures often than you can from successes. And always when you do your work, make sure it's the highest quality you can, okay? You don't want to be known for doing a lot of things that are superficially done. You want to really dig in and operate at the highest level of quality. It's important that you build networks. Some of my greatest friends I met as peers during graduate school, and now we support each other in many ways throughout our careers. Also identify mentors and serve as a mentor to others. And get involved in research as early as you possibly can. And for those of you who are interested in the RU program at A&M, I'll show you in just a moment. The deadline for applications is February 15th, so it's just a few days away. But ultimately, as you go into your lives, you know, try to impact society. Try to think of how you can do things that will be positive to benefit society. Again, the RU program at Texas A&M is focused on sustainable chemistry. There are a lot of different projects that are available, a fairly decent stipend, and like I said, the deadline is February 15th. I sent an email this afternoon to see if there can be an extension. So if you're interested in it and you won't be able to make the February 15th deadline, send me an email and I'll see if we can get you an extension on that. Okay, so here's my background. So I was born in a small town in Oregon, and someone I met today, Savannah, I think, grew up in a smaller town than I did, right? My town I thought was small, but I think yours was about 10 times smaller. But it's actually a really great opportunity to grow up in a small town, especially in a beautiful place like Oregon. You can see some of the images here. It was basically a logging community. There were 2 mills and a whole bunch of loggers. My dad was a millwright. But what I learned was how to work hard. You never did anything part way. You also learned how to survive. So if I would have fallen off the back of this motorcycle, I think I would have had some issues. But middle child, any other middle children? Yeah, we're always struggling for attention, right? Yeah, we're probably the brats, but we don't always admit it. When I went to school, I could only stay in the state, and my parents didn't have a lot of money to send me like to a private school, so my options were Oregon State or University of Oregon. Oregon State was further from home, so that's where I went. It also had a much stronger chemistry program. So graduated with a BS in 1988. I started in the lab in research, actually as a glassware washer to begin with, as a freshman. I think it was just a fantastic experience over the years. I got to go back there about a year or so ago with my 2 sisters, and so that's quite a bit of different photo than what you'd seen before. From Oregon State, I applied to, I don't know, probably 10 to 20 graduates, probably 15 to 20 graduate programs. saw what acceptances I got and then made a decision from there to go to Cornell, and I couldn't have made a better decision. I had the opportunity to work with Jean Frichet on dendritic macromolecules. Those are tree-like molecules. It was like the heyday for macromolecular topology control. And from that, graduating in 1993, I was able to go directly into a faculty position. I kind of wanted to do that because my oldest son was born in 1990, so he was 3 years old when I was graduating with my PhD. And I didn't want to go for a postdoc somewhere, start him in school and things, then have to move again in just a couple of years. So I had the fortune of starting at Washington University in St. Louis as an assistant professor when I was, this is being recorded but not put on the web, so when I was going through the tenure process, I think someone at another school must have seen my package, and then that school tried to hire me, which meant that WashU had to retain me. So I got to be promoted directly to full professor without being an associate professor. I know, associate professor sucks, I'm sorry, Courtney. Then was installed as a McDonald professor in 2006. And then this fantastic opportunity came along to move to Texas A&M in 2009, and I've been there now for almost 10 years. And I have to tell you, Texas A&M is a fantastic place. If you guys are interested in graduate school, apply. It's a great place. Just come and visit. I think you'll find it a bit intoxicating. Some people think it's like a cult, but it's really not so much. And then I have to say, you know, nothing I've done would be possible without support, right? Support of mentors, support of peers, but really support of my students, my research program, my colleagues. I have friends all over the world, and we come together at various times, and it's just such a really great experience. But also support of family. So I have a large family down in Texas, 3 wonderful boys, and you know, it's just such a great opportunity. Make sure you know that you can do anything you want to do. Don't feel like you have to make sacrifices one way or the other. So what you have to do is find that balance and figure out what works for you. So here's what works for me. The first thing is that I have this pretty strict rule that work is work and home is home. So when I'm at work, if someone comes to my office and says, "Are you busy?" I just think to myself, you know, if I weren't busy, I should go home. But you know, I try not to be rude. But you've got to work hard when you're working, and then disconnect when you're ready to disconnect, and have that opportunity to do both. We also have a motto in my family that we have to work first, then play. And so we do so. This is my youngest son. He was a power lifter at College Station High School. And then realize that you can't get everything done, but do everything you can to the best of your ability. Be selective. I know you guys have to get involved in all kinds of extracurricular activities. At some point you're going to have to say, I can do these things really well, and this is what I'm going to enjoy doing, and then let some of the other things go. In my case, I want to travel less. That still hasn't worked out. But one of the travels I do that is really important, and think about this maybe in the future, is just to take a holiday once a year or once every 2 years. And I think I learned more about my children on holidays than I did, you know, with all the hustle and bustle of daily life. So that's where I'd like to leave it. I'd like to take any questions if I haven't consumed all of the time, but thank you so much for your attention. Thank you, Courtney, for the invitation.
All right, that was super cool. Can you go back to the water where there was oil on the water and oil underneath? Because it looked like you were going to use your stuff there, and I wanted to hear about it.
Yes, so, okay. Yeah, so in the case of May's video, she had lyophilized her powder. So when she dropped it in, it was floating on the surface. But if we don't lyophilize the materials, they're assembled in water, and if we add a solution of these particles in water, they migrate throughout the entire water column, and they can collect the oil underneath the surface. And then what happens when they fill with oil, they float to the top. It's really amazing, yeah.
So have you actually tried that out? outside in a pool of water?
No, not outside. Yeah. We have done, not for these systems, we together with Bill Johnson, who's at the University of Utah, we did our first deployment in a gravel column at Notre Dame. They have this channel system, and we had labeled particles, and he would drip them in and have this flow going, and he tracked, at like 10 feet, 20 feet, 30 feet down to follow the particles to see how they migrate, in that case, in an attempt to clean up, say, groundwater pollution. But we haven't deployed anything in like a water body. Yeah.
So are there any like procedures, I guess, or hoops you have to go through in order to be able to use it out in the environment?
For like the EPA and things, yeah.
Mhm.
Yeah, I'm sure there are, and we're not yet to the point of doing that. And in fact, based on the cost analysis of these particles, we wouldn't use them to like put into the Gulf of Mexico, like was our motivation. Rather, we're expecting that maybe these would be deployed just in advance of water intake sites, right? Because water is used for cooling water, water is used for drinking water in a lot of places. And if we could deploy them in such a way that they could be captured through some kind of a pipe system that would have magnetic responsivity, then that might be something that would be, at least more contained. Yeah.
So on a larger scale, how would you utilize a magnet to retract them?
So I was looking into this, and there was a company in Australia for a while that was working on something similar to this, and based on different compositions. And they had built some big apparatus that was like a recycling, circulating thing that had like magnetic coils in it that somehow captured things. But I don't know. We would need to partner with an engineer to do that. But yeah, it's definitely possible.
So it is after 7, so I know that some of you may need to leave, so feel free to do so, but I'm sure Dr. Wooley would be willing to hang out for a few minutes afterwards if you have additional questions for her.
Absolutely.
Let's thank her one last time.